Ever wondered how your favorite ice cream goes from mood to mouth in a high-tech factory? Dive into this mouth-watering step-by-step guide to find out. Ice cream, the creamy delight that brings joy to millions, is more than just a frozen treat. It's a marvel of modern food engineering. Behind every scoop lies a sophisticated, high-tech process that blends science, technology, and artistry. This 6,000-word guide takes you on an in-depth journey through the fascinating world of ice cream production in a state-of-the-art factory, from sourcing raw ingredients to packaging the final product. We'll explore each step with technical precision and engaging insights, ensuring you leave with a newfound appreciation for this beloved dessert. Ice cream is a complex emulsion of fat, water, sugar, and air stabilized by proteins and emulsifiers. Its smooth texture, rich flavor, and endless variety are the result of precise engineering and cutting-edge technology. High-tech ice cream factories operate like well-oiled machines, producing thousands of gallons per hour while maintaining strict quality and safety standards. These facilities combine automation, robotics, and advanced analytics to ensure consistency, efficiency, and innovation. The global ice cream market is booming, valued at over $60 billion in 2024, with consumers demanding premium, plant-based, and low-sugar options. Modern factories are equipped to meet these trends using everything from cryogenic freezers to AI-driven quality checks. Let's break down the process step by step to uncover the magic behind your favorite frozen treat. To step 1, sourcing and testing raw ingredients. The journey begins with raw ingredients, each carefully selected for quality and consistency. The primary components of ice cream are milk and cream. The backbone of ice cream, providing fat and protein. Factories source dairy from trusted farms, often using milk with 3 to 4% fat and cream with 30 to 40% fat for premium variety. Sugar, typically sucrose or glucose syrup. Sugar sweetens and lowers the freezing point, ensuring a smooth texture, stabilizes, and emulsifiers. Ingredients like gum, carrageenan, and mono and diglycerides maintain structure and prevent ice crystal formation. Flavorings, vanilla, chocolate, fruit purees, or natural extracts add distinctive taste inclusions. Chunks like cookies, nuts, or swirls of caramel enhance texture and flavor. High-tech factories use spectroscopy and chromatography to test ingredients for purity, fat content, and microbial safety. For example, near-infrared NIR spectroscopy analyzes milk composition in seconds. Ensuring it meets standards, suppliers must comply with regulations like the FDA Pasteurized Milk Ordinance or EU dairy standards. Sustainability is key. Many factories partner with farms practicing regenerative agriculture or source plant-based milks, oat, almond for vegan options. Blockchain technology is increasingly used to trace ingredients, ensuring transparency and ethical sourcing. 3. Step 2. Creating the ice cream base. Once ingredients pass quality checks, they're blended to form the ice cream base. This step occurs in stainless steel mixing tanks equipped with high shear mixes. A typical recipe might include 50 to 60% water from milk to 15% fat from cream and 20% beef sugar for 10% non-fat milk. Solid 0 to 0.5% stabilizers, emulsifiers. The process is automated with programmable logic controllers, PLCs, ensuring precise measurements. For example, load cells weigh ingredients to within 0.1% accuracy, and flow meters regulate liquid additions. The mix is heated to 40s and 50 Dix to dissolve sugars and stabilizers fully. Factories use recipe management software to adjust formulations for different products, such as low-fat or high-protein ice cream. Data from previous batches is analyzed to optimize sweetness or creaminess, ensuring consistency across millions of pints. 4. Step 3. Pasteurization and homogenization to ensure safety and shelf life. The ice cream base undergoes pasteurization and homogenization. Pasteurization, the mix is heated to kill pathogens like Listeria or Salmonella. High-tech factories use high-temperature, short-time HTST systems, heating the mix to 72 degrees for 15 seconds. Plate heat exchangers maximize energy efficiency, recovering up to 90% of heat homogenization. The mix is forced through a high-pressure valve, 1500 2500 PE/PSI, to break fat globules into smaller particles. 2 microns. This creates a uniform emulsion, preventing cream separation and ensuring a creamy mouthfeel. Multi-stage homogenizers enhance efficiency. Both processes are monitored by SCADA systems, supervisory control and data acquisition, which log temperature, pressure, and flow rates in real time. Any deviation triggers alarms, ensuring compliance with food safety standards like HACCP 5. Step 4. Cooling and aging the mix. After pasteurization, the mix is rapidly cooled to 4°C using shell and tube heat exchangers. Rapid cooling prevents bacterial growth and prepares the mix for aging. Aging involves storing the mix in refrigerated tanks for 4 to 24 hours. During this time, fat globules crystallize, improving structure, stabilizers hydrate, fully enhancing viscosity. Proteins stabilize air bubbles for better overrun air incorporation. High-tech factories use agitated aging tanks with precise temperature control. Some employ ultrasonic sensors to monitor viscosity, ensuring the mix is ready for freezing. Aging is critical for premium ice cream, as it delivers a smoother, richer texture. 6. Step 5. Flavoring and adding inclusions. Before freezing, flavorings and inclusions are added. Factories use inline dosing systems to inject liquid flavors like vanilla extract or cocoa slurry for complex flavors. Micro-encapsulation protects volatile compounds, ensuring consistent taste inclusions like cookie dough or fudge swirls are added via variegators or fruit feeders. These machines precisely control the size and distribution of chunks using servo-driven pumps for accuracy. For example, a variegator can inject caramel swirls at 10 to 20% of the total volume, creating visually appealing patterns. Machine vision systems inspect the mix for uniform inclusion distribution, rejecting batches that don't meet standards. This step is where creativity shines, as factories experiment with trends like matcha chunks or edible glitter. 7. Step 6. Freezing and aeration. The heart of ice cream production is continuous freezing, where the mix is frozen and aerated. This occurs in a scraped surface freezer, a cylindrical chamber cooled to 5 degrees to 7 digs. Key processes include freezing. The mix is churned against the freezer's walls, forming small ice crystals, 50 microns liquid. Refrigerants like ammonia or CO2 maintain low temperatures. Aeration. Air is whipped into the mix, increasing volume by 100% known as overrun. Premium ice cream has lower, overrun 20-40% for a dense texture, while soft serve has higher overrun 100% dasher action. A rotating dasher scrapes frozen mix from the walls and blends in air. Variable speed motors adjust dasher speed for different textures. Advanced freezers use cryogenic cooling liquid nitrogen at 196 degrees Celsius for ultra-fast freezing, minimizing ice crystal size. IoT sensors monitor freezer performance, predicting maintenance needs to prevent downtime. The semi-frozen mix exits at 5 degrees Celsius with a soft serve conceal. Consistency, ready for shaping or hardening. 8. Step 7. Shaping and hardening. The semi-frozen mix is shaped into pints, bars, or cones using forming equipment for pints. Rotary fillers dispense precise volumes for G4, 73 ml into containers for novelty items like sandwiches. Extrusion lines shape the mix, which is then cut and coated. Hardening solidifies the ice cream at 30 degrees to 40 digs in blast freezers. High-tech factories use spiral freezers, where conveyor belts move products through a continuous cold airstream. Hardening takes 2 to 4 hours, ensuring ice crystals remain small for a smooth texture. Thermal imaging cameras monitor product temperature, ensuring uniform hardening. Some factories use robotic arms to stack hardened products, reducing labor costs and contamination risks. 9. Step 8. Packaging and quality control. Packaging is both functional and aesthetic. Ice cream is packed in laminated cartons, plastic tubs, or composite cans to protect against moisture and freezer burn. Modified atmosphere packaging map replaces air with nitrogen to extend shelf life. Metal detectors and X-ray scanners check for contaminants like metal shards or plastic. Machine vision systems inspect seals and labels, ensuring barcodes are scannable and branding is flawless. Quality control involves sensory analysis, taste, texture, and lab testing. Fat content overrun, for example. Gas chromatography, mass spectrometry, GCMS verifies flavor authenticity. Random samples are stored for shelf life testing, simulating months in a freezer, 10-step 9, storage and distribution. Finished ice cream is stored in automated cold storage warehouses that transfers to 20-degree, 230 digs. Automated storage and retrieval systems, ASRS, use robots to stack pallets, maximizing space and efficiency. RFID tags track inventory, ensuring first in, first out. FIFO rotation. Distribution uses refrigerated trucks with GPS and temperature monitoring. Factories partner with logistics firms to deliver to retailers within 2,448 hours. Maintaining the cold chain. Blockchain ensures traceability, reassuring consumers of product integrity. 11 innovations in high-tech ice cream production. Modern factories embrace cutting-edge technology, AI and machine learning. Predictive models optimize recipes and detect effects. For example, AI analyzes ex posts to identify trending flavors like lavender, honey, 3D food printing, experimental systems, print custom ice cream shapes like edible logos. Plant-based innovation, enzymatic processes improve the creaminess of oat or coconut-based ice cream. Sustainable tech factories use solar panels and closed-loop water systems to reduce environmental impact. These advancements keep ice cream exciting and accessible, meeting diverse consumer needs. 12 environmental and ethical considerations. Ice cream production has environmental challenges, including energy use and packaging waste. High-tech factories are responding energy efficiency, heat recovery systems, and LED lighting cut energy use by 20 and 30%. Sustainable packaging. Biodegradable tubs and recyclable films are gaining traction. Carbon footprint. Some factories offset emissions through carbon credits or reforestation ethically. Factories ensure fair wages for farmers and ban child labor in supply chains. Certifications like Fair Trade or Rainforest Alliance build consumer trust team. Conclusion, the future of ice cream manufacturing. The ice cream industry is a blend of tradition and innovation. High-tech factories deliver consistent quality at scale using automation, AI, and sustainable practices. As consumer preferences evolve, expect more personalized, eco-friendly, and health-conscious options. Next time you enjoy a scoop, remember the intricate process behind it. From farm to freezer, ice cream isn't just a treat. It's a testament to human ingenuity and technological progress.